So if you recollect, we were talking about amplitude modulation. We have looked at the important properties of an amplitude modulated signal and looked at the time domain waveform, looked at the frequency domain spectrum, and we were now discussing the demodulation of amplitude modulation. And what we discussed so far was that by the insertion of this carrier at the transmitter along with the modulated signal, along with the DSPSC component, if we make sure the envelope of the resulting signal follows the message waveform, the shape of the message waveform, then we have an advantage, right? This could of course be done by making sure that we have sufficient carrier inserted into the transmitted signal, in which case we basically the modulation index should be less than 100%, right? Should be less than 1. If it becomes more than 1, essentially that shape following property will not be there, and we will not be able to have the advantage of using a very simple demodulator. And the demodulator structure was extremely simple. This was a circuit we discussed very briefly. We'll discuss it in more detail now, where you have a simple diode followed by a resistor RL in parallel with a capacitor C. And our premise is that if at the input you apply the message signal, the modulated signal x of t, the amplitude modulated signal x of t, the output z of t will be proportional to the message signal or message waveform m of t, right? And if this works, as we indicated briefly how it could, the advantages of this simple circuit are that we don't require any complex circuits for synchronization of the local carrier with the incoming carrier. So no synchronous carrier is required, and thereby the receiver becomes a much cheaper version. Now, this was a very brief introduction to how the demodulator works. It's again a repetition of what we did that day. So what we said was that the diode will conduct only in the positive half cycles of the carrier, right? Even there it does not always conduct, right? In the beginning, when the diode is when this positive half cycle comes, the diode conducts, and if we assume that the charging circuit for the capacitor has a very small time constant, then the capacitor voltage will more or less follow the carrier signal that is coming in during this half cycle, right? So it will keep on getting charged to the incoming voltage till it reaches the peak value. So when it reaches this peak value at this stage, and when the input voltage now drops, this diode becomes reverse biased, because this point is at a higher voltage than this point. So there is no conduction of the diode. The diode remains reverse biased during this falling portion of the carrier half cycle, and during this period the capacitor discharges through this load resistance, through this R sub L, and let's say there is a certain discharging time constant which is not too fast. The discharging, we don't want the discharging to be too fast, so that it more or less stays at the constant value that it had charged to, right? Except that it decays just a little bit, right? And then the next half cycle comes in. At this point, again the diode becomes forward biased, again the capacitor starts charging, charges to the new peak value, and this cycle of operation repeats itself to produce an output waveform which looks like this, which looks like the black profile I have shown here, right? And thereby you can see, of course, this diagram is highly exaggerated in the sense that the carrier cycles will be much more closely spaced than I've shown in this diagram, right? So actually what you will see is not such a wavy envelope, but a fairly smooth envelope, which can be smoothened still further by a suitable low pass filter if required, right? So that's the basic principle. Now for this to work, are there any conditions that we should satisfy? Obviously yes. Let's look at the charging path. The charging path is through, let us say, some source resistance that you might associate with the input. After all, the input is a voltage source coming from somewhere, maybe from an antenna or from some previous stage of the some amplifier previous to the demodulator, right? So there would be a source resistance associated with the waveform x of t. Let's say the source resistance is R sub s. And let us say the forward bias, during the forward bias the diode behaves like a simple resistor with a resistance of a small value of the resistance equal to R sub f. So we can call it the forward bias resistance of the diode, right? Typically both the source resistance, the source impedance and the forward bias resistance are small values, right? And what will be the charging path? The charging path is essentially this. This is the charging path, right? The capacitor charges like that. Assuming that RL is sufficiently large, it will hardly affect the charging path. If you assume that, RL is, let's say much greater than RS plus RF, right? The charging path, charging of C has a time constant. What is the time constant associated with it? Given by RS, R sub S plus R sub F times C. And what would you like this charging time constant to be? Large or small? Extremely small, right? Can we quantify this, how small it should be? It should be much smaller than, let's say, the half cycle duration, or the, let's say, cycle duration of a carrier wave, so that it follows the carrier as it comes, more or less. Yes, please.
Sir, why are we saying that the diode will not conduct while the peak is falling?
Isn't that obvious? The question is, why would the diode stop conducting at in this interval? That's because the output at this point, the voltage here is now higher than the input voltage, right? When does the diode conduct? If the, let's say, suppose this is a PN junction diode, if the P side is at a higher voltage than the N side, right, then only it conducts, isn't it? It's a very elementary operation of the diode. Is that clear? Okay.
So what is the RL?
RL is this load resistance that I have talked about.
Then why are we saying that RL is far greater than RS plus RL?
I just explained, because if you assume that, then this would not come to the picture of the charging time constant. This will be so high that the current will hardly flow. The charging current will hardly flow through this resistance. Most of the current will be used to charge up the capacitor, right? And the charging time constant therefore would not have to worry. We don't have to worry about the value of R sub L in calculating the charging time constant. If you want to calculate the charging time constant more accurately, what will it be? It will be, the resistance involved will be RS plus RF in parallel with RL. So all we are saying is RL is much larger than this, so therefore the parallel combination behaves more or less like RS plus RF itself, right? So that's another way of looking at it. So the point is that for the charging time constant, the condition that we should have is that this time constant is much less than the reciprocal of f sub c, which is the time period of the carrier wave, right? It should be much smaller than that, so that the capacitor immediately charges the moment diode starts to conduct, right? It follows the cycle, half cycle of the carrier wave as it comes during the positive half cycle, right? So this is one condition that is required. The second condition is regarding the discharge. What would you like the discharging time constant? What is the discharge path? Let's come back to this. Through RL. So what is the discharging time constant? RL times C, right? So what would you like RL times C to be? Should it be a large value or a small value? It should be large. It should discharge slowly, right? So RLC should be much greater than 1 by FC. But this is one aspect. This can lead to a situation which is not desirable. Do you appreciate that? Let's look at this picture once again. Suppose your time constant, discharge time constant is very slow. Let me take a different color now. It can happen that the discharging is very slow. Let's say, suppose it is very slow here, right? Suppose it is so slow that the next peak comes at a lower value than the amount to which the previous peak has discharged. Right? Is that good or is that bad? It is bad because you are not following the envelope, right? So this would lead to a kind of clipping. You would miss all these variations in between, right? So while this discharge time constant should be slow, it should not also be so slow that it does not follow the fast fluctuations that might take place in the envelope itself, right? This envelope fluctuation here is much faster than the rate of discharge of the capacitor, and therefore there is a kind of distortion that will come up in the envelope which we call the clipping distortion. Right? And which we should avoid if we want to get a faithful reproduction of the envelope. Right? So what condition should be satisfied for that? While this time constant should be much larger than 1 by FC, that is perfectly fine, but it should be much smaller than the rate at which the highest rate at which the message signal itself can vary, right? The moderate signal itself can vary. And what would be the highest rate of message signal variation depend on? The bandwidth of the message signal, the highest frequency present in the message signal, right? So let us say the bandwidth of the message signal is B, therefore the highest frequency present in it is B, and therefore the time interval of interest is 1 by B, right? So what we would like to have therefore in addition is that RLC should be much less than, complete the sentence, 1 by B. These two conditions we can put together to say that right, the time constant R sub L times C should be much less than 1 by B, but should be much greater than 1 by FC. So if these two conditions are satisfied, by and large you will have a system which works nicely, right? So these are the two conditions that we need to satisfy. Any questions? Any questions?
So won't it depend upon the amplitude or not?
It will depend on the amplitude. Basically, we have captured the relation, the approximate relation. The details are definitely a little more involved. Right? The question was, would this also depend on the amplitude variation of the envelope? Right? Actually, most of it is captured. Most of those variations are captured by 1 by B, right? But there is some amplitude dependence which is not captured by these equations. We will discuss them separately, let's say in some problem session. Right? You see here? No. Why FC plus B? You are trying to track the envelope. FC doesn't come into the picture. You are trying to track the envelope. Envelope is nothing to do with FC. The envelope is entirely a property of the message waveform M of t, right? F sub c has nothing, the carrier frequency has nothing to do with it, right? You just want to make sure that this condition does not arise. right? You want to make sure that while the rate of discharge is slow, it is not so slow that you capture the fast fluctuations in the envelope itself, right? So you are comparing this rate of variation with the rate of variation of the message waveform, the envelope. Is that clear? Right. So this carrier frequency does not enter into the picture at this stage. Okay. So that is what the envelope detector is all about. So this is what we call the diode detector. It has various names. We also call it the envelope detector. And as you can see, just with these three components, a diode, a resistance of a sufficiently large value, and a capacitance, we can build a very simple demodulator, right? And that's what most of your AM receivers do, right? That you use in your homes or whatever. Okay, to wind up the discussion on amplitude modulation, we'll take up a small example. Let's say our message signal is a pure sinusoidal signal of frequency f sub m. So that your modulated signal x of t is given by, what will it be given by? Something like this, right? 1 plus mu times the message waveform m of t into the carrier, right? So the first term is the carrier component, the second term is the DSP-SC kind of component, which together forms these two components, when added together, forms the AM signal with carrier, right? So if you want to if you want the envelope of the signal to follow the message waveform, what should be the condition on mu? Mu is here, it should be less than 1, right? The modulation index should be less than 1, or the percentage modulation should be less than 100%. So for the envelope to follow M of t here is this. What do the signal look like? What do these two signals look like in the frequency domain? What is the message spectrum like? Impulses at f sub m and f minus f sub m. After modulation, the spectrum of the modulated signal x of f, you will have these components at fc, f sub c plus f sub m, f sub c minus f sub m, and also there will be a carrier component, right? Similarly, there will be components at minus fc plus fm minus fc and minus fc minus fm, right? This is what the spectrum will look like for this signal. Let's do some power calculations now, and therefore power efficiency calculations, right? To do that, let's look at how much power is carried by the carrier and how much power is there in the sidebands. Which are the sidebands in this case? These are the two sidebands. This one is the upper sideband, this is the lower sideband. Actually, these two together, this and this together, constitute the upper sideband. This and this constitute the lower sideband, right? So if you were to write this expression in terms of the various components that are present in the signal, then we have, it is the carrier component, which is AC cosine 2 pi fct, and by using the trigonometric identities, you can write the rest of them in terms of the two sideband components. The upper sideband will have an amplitude mu AC by 2, and the signal there is 2 pi fc plus fm t, right? Similarly, you have a lower sideband which of amplitude half mu AC plus sine 2 pi fc minus fm t, right? Just by simple trigonometric identities you can write this. Now, how much power is carried by the carrier? So, what is the carrier power? If you keep this there, carrier power will be AC square by 2, A sub c square by 2. What about the upper sideband power? This will be 1 by 8 mu square A sub c square, right? Half of the square value of this amplitude, right? Similarly, the lower sideband power would be also the same. And then you can calculate the power efficiency now. What is power efficiency? How should we define power efficiency? The useful power transmitted as a fraction of the total power transmitted. What is the useful power transmitted here is this plus this, the two sidebands, power in the two sidebands. 1 by 4 mu square A sub c square upon 1 by 4 mu square A sub c square plus half A sub c square, right? Which A sub c square cancels off, and this simplifies to mu square upon mu square plus 2, right? And therefore, that is the efficiency that you will have, power efficiency you will have for a modulation index of mu. And what is the best power efficiency you can have will be obtained by mu equal to 1. Then you take mu equal to 1, right? And what is the power efficiency there? So 33% approximately for mu is equal to 1. Okay. So if you were to plot this power efficiency in the form of a picture, not power efficiency but various powers that we had talked about as a function of mu, let us say, and the profile of the carrier power comes down like that, right? If you have mu equal to 0, all the power is in the carrier, right? When you take mu equal to 1, 67% of the power is in the carrier, right? As far as the sidebands go, at mu equal to 0, there is no power in the sidebands, and at mu equal to 1, 33% power is in the sidebands, right? So that's the profile that you have. This discussion we have carried out when the modulating signal was a pure sine wave, right? One can prove that for more general kind of waveforms, modulating waveforms, the modulation of the power efficiency can be increased, but under no circumstances it will be more than 50%, like we discussed earlier. Okay. Now we have so far discussed two kinds of amplitude modulation. Which are the two kinds? DSBSC, and for want of a better name, the second kind with carrier is usually referred to as DSB-AM. Okay, that's a normal name, but a more precise way would be to say double sideband with carrier, right? But that's a normal way we normally refer to it. What are the pros and cons of these? This is efficient in power and bandwidth efficiency is same for both of them, right? Both of them would require twice the message bandwidth as the final transmitted bandwidth, right? So there is no difference in the bandwidth efficiency of the two waveforms. However, in terms of power efficiency, Which one is better? DSPSC is much better, right? But we have said that in some situations we may be ready to sacrifice power efficiency for an economical receiver, right? And when you want to do that, like in broadcast applications, you can choose DSPSC. However, wherever power efficiency is important, right, like in point-to-point communication, not in broadcast applications, you would always go for DSPSC rather than DSPA, even at the cost of a more complex receiver, which requires synchronous carrier.
In the case of DSP, as you said, the zero crossing, we used to lose the signal.
No, we don't lose anything. I think there is. Please raise some of these basic doubts that you have during the tutorial classes, so that we can take care of those situations. If we had lost any signal in any way, then how would we be able to reconstruct it? We have shown that synchronous demodulation completely recovers the signal, so we not lost anything. We're just looking at the characteristic of the message waveform, of the modulated waveform, which has some properties.
So, but every second the phase was changing. So wherever the phase changes, we cannot get the amplitude as we got in the case of DSP.
I think you are confusing. The question is in fact, I have not really fully understood the question, but roughly he's trying to imply that because there is a phase reversal at zero crossing, we have lost the message. No. That's just a property of the modulated waveform, right? Yes, if you were to say that whether we can recover the message back by using envelope detection, the answer is no. We cannot recover the message back from a DSPSC waveform by using a diode detector, because what will the diode detector give you? Not MT, but modulus of MT, right? So certainly we cannot recover the message waveform by using the diode detector, but we have already seen that we can recover it by using synchronous demodulation, right? That is the price we have to pay for power efficiency that we will get here. Yes, please.
Sir, I have a question on the power we just calculated.
Yes.
On the numerator we had 1/4, but the lower sideband you said isn't required, so should we just have half?
No, we are only talking about the modulation that we are working with right now. If we remove the lower sideband or the upper sideband, we are working with a different kind of modulation, which we have to still discuss. Certainly that is something that one can do. One can increase the power efficiency further by removing one of the sidebands which is not required anyway, right? I think that is your point. Certainly that is correct, and we will discuss it separately, right? We have still to come to that situation. In fact, I am leading towards that shortly. Is that okay? Can I proceed further then? So let me come back to the discussion regarding these two. One of the nice properties of the suppressed carrier DSP waveform was, if you recollect, that in fact it was not a nice property that we introduced. We said that it is a disadvantage of DSPSC, that if your local carrier is out of phase with the incoming carrier, you will tend to lose the signal, right? Let's say there is perfect frequency synchronization, but there is a loss of phase synchronization. Then the output is proportional to mt cosine theta, where theta is the phase difference. So much so that if theta is pi/2, the output will be 0, and this we consider as a disadvantage of DSPSC. Actually, we can convert this disadvantage into an advantage. Can you see how? Anyone can make a suggestion to that? Can I convert this disadvantage into an advantage of some kind?
You can select signals.
I can put two signals on the same carrier, one using a cosine omega ct carrier, the other using a sine omega ct carrier, and if at the receiver I ensure that there is a perfect phase synchronization for each of them, I can separate out the two without interference from the other, because of the nulling effect of the output due to a phase quadrature relationship between the carriers, right? So this is a very nice thing one can do, which is called quadrature carrier multiplexing. That is, you can put two signals on the same carrier, right? Normally we don't think of putting two signals in the same carrier. So we are here using the nulling effect of the coherent or synchronous detector to advantage.
This is what we use in 2PSK.
Sorry?
This is what we use in 2PSK though. Phase shift key point coding.
Let's not talk about PSK at the moment because we are talking of analog modulations, whereas PSK etc. are digital modulations, right? Yes, it is relevant. Whatever what we are discussing here is relevant to that, but I would not like to bring in that at this point. So we have two DSBSC waves. With different messages, carrying different messages. And both of them will be transmitted in the same bandwidth, isn't it? The spectral occupancy of both the carriers would be, both the modulated signals will be in the same FC plus minus B hertz, right? So if you can do that, what would you do? You would increase your power efficiency by a factor of 2, not power efficiency, bandwidth efficiency by a factor of 2. In the same bandwidth you are transmitting only one message, now you are transmitting two messages. So basically what we are saying is, suppose I use a modulated waveform which is x of t equal to a sub c m1t cosine omega ct plus a sub c m2t sine omega ct, right? I am transmitting both of them together at the same carrier frequency, right? Then I can reconstruct m1t separately independent of m2t and vice versa, right? So basically I have multiplexed two message waveforms onto the same carrier. So this we call quadrature carrier multiplexing or quadrature amplitude modulation. It's also called quadrature amplitude modulation, QAM. Okay. To put it in the form of a figure, you have a multiplier for AC cosine omega ct. Let's say you have a 90-degree phase shifter here. Your message signal m1t comes here, and this is your modulated signal m1t times AC cosine omega ct. Here you will have AC sine omega ct. This is a 90-degree phase shifter. Right? And the second message signal is coming here, m2t. You multiply this with AC sine omega ct, and these two are added together and transmitted as the multiplex signal. So this is a multiplex signal. And how will you demultiplex them? How will you separate them out of the receiver? Your multiplex signal is coming in. Just like your synchronous demodulation, you will have two synchronous demodulators. One in which the local carrier is AC cosine omega ct, right? Followed by low pass filter. Remember that? That is a synchronous demodulator, coherent detector. A synchronous demodulator is also called a coherent detector, unlike the envelope detector, which is not coherent, right? Which does not require a phase coherence of the carrier and the incoming signal. And similarly, if I use a second demodulator, a second coherent detector, this should be AC sine omega ct. Followed by low pass filter. So what will this give? the message waveform M1t. This will give M2t, right? And there will be no interference, because if since there is a phase difference of 90 degree between the second carrier and this carrier, this will not produce any output in this channel, right, in this path. Similarly, the M1t will not have any component in this path, provided of course we have perfect phase coherence, that is, its cosine omega ct is in phase with the cosine omega ct component of the incoming signal, and sin omega ct is in phase with the sin omega ct component of the incoming signal. So you require perfect phase synchronization or perfectly coherent carrier as before, right? So if you are ready to pay this cost, always, in most systems, most engineering systems in general and communication systems in particular, whatever you typically achieve, it will be at the cost of something else, right? So the cost here is additional complexity, but if you are ready to pay for the cost of that additional complexity, what do we have? We have good bandwidth efficiency, right? The same message bandwidth gets used to transmit two messages rather than one. That's the advantage.
You can transmit more than two also with different phase differences.
Not in this context, right? I think you have something else in your mind which is not relevant here, right? We are talking of analog modulations here. In the context of analog modulations, that's all we can do, right? I have a small request. Please do not mumble. There's a lot of sometimes mumbling in between. I think it's not good for the recording system. It picks it up, right? It of course disturbs me also. So I think they'll have to edit this portion now because of this fact. Okay. So we have looked at the DSB SC, DSB AM and QAM. These three kinds of modulation, amplitude modulations. What next? Is there any variation? Yes, indeed. In fact, it was pointed out just a few minutes ago. While we can achieve good simple demodulation using DSP AM, the power efficiency of this is very poor, right? In fact, the power efficiency needs to be definitely improved if possible. And one simple way of doing that is removing information which is redundant, right? And that is by removing one of the sidebands, right? So in fact, if you do that, you will kill two birds with one stone. You will improve your power requirements and also your bandwidth requirements, right? So obviously that is the right thing to do if it can be done, and if you can work out suitable methods of both transmitting as well as demodulating such signals, right? This class of modulations are known by the name of suppressed sideband modulations. Okay. And they are motivated by the fact that the two sidebands carry same information, identical information. So we can suppress one of them either completely or at least partially. Okay. Now why I'm giving these two options is because there are pros and cons of each of them, right? At times it does make sense to talk of suppressing one of the sidebands completely. At times it does not, right? But if you still want to save on bandwidth, we'll say okay, if you can't suppress it completely, can we suppress it at least partially so that we can save on some bandwidth, right? We'll see examples of both the situations as we go along. Okay. So when we suppress it completely, basically one of the two sidebands goes, and that leads to what is called single sideband modulation. Okay, because you are either transmitting the upper sideband or transmitting the lower sideband. When you suppress it only partially, what you typically do is you transmit more or less the entire one of the entire sidebands, more or less, and a small portion of the other, also called a vestige of the other, right? And therefore we call that by the name of vestigial sideband modulation. Okay, so there can be two kinds of suppressed sideband modulations: the single sideband modulation or the vestigial sideband modulation. Right? So we'll first discuss the single sideband modulation. Now, in the single sideband modulation, as the name implies, what you have to do is first generate. Sorry, let me take a fresh page. You start with your message signal empty, have a product modulator which multiplies with the carrier AC cosine omega CT, right? And what should you do next? This will generate the double sideband signal. You want to remove one of the sidebands. You have to have some kind of a filter, a suitable sideband filter. Right? And that will be now your message waveform X of t, your transmitted waveform or modulated waveform X of t, right? So that's your SSB modulator. Let's look at the whole thing in the frequency domain. Let's say this is your message waveform, the spectrum of the message waveform, MF, right? And the modulator output, if at this point you would have got something like this, right? Right? This would have been the spectrum of the double sideband signal that is coming here. Now after you put the sideband filter, what are you retaining? You are retaining either this right? Either you are retaining this part or you are retaining the other part, right? So if you want to retain this part, what should you do? What kind of a sideband filter you should have? A high pass filter, right? Or we should have a band pass filter here, which will only pass this portion of the spectrum and reject everything else. So either a high pass filter, let's say theoretically a high pass filter will do. In practice we'll of course use a band pass filter, right? So theoretically a high pass filter will be able to separate out the upper sideband from the lower sideband, right? So you require a filter with this kind of characteristic, right? Whose transfer function is 1 for f greater than fc and is 0 between minus fc to plus fc. Is it clear? For mod of f greater than fc, the transfer function is 1, so it will pass off this spectrum to the output, and this spectrum will get attenuated or suppressed, eliminated, right? If you want the lower sideband, you should have a low pass filter with a cutoff frequency of f sub c, right? So depending on whether you want the lower sideband or the upper sideband, you can use an appropriate filter, which ideally could be either high pass or low pass. Is it clear? In practice, we don't use low pass filters of such large bandwidth 0 to FC or such high pass filters, because in any case the signal has a finite small bandwidth, right? So it's more convenient to use band pass filters, either of this kind or of this kind, right? That will be the actual, but for theoretical discussion here, it is preferable to think in terms of high pass and low pass filters, as we will soon see. Suppose we retain the upper sideband. Now how do I get this Bessel signal back? How do I do the demodulation? Can anyone suggest? Because if I can't demodulate, then this whole exercise is a wasteful exercise. It doesn't help anything, right? What should I do as a demodulator? Any answers? The demodulator remains the same synchronous demodulator that we had for DSPSC. Absolutely no difference. Convince yourself. So what I'm saying is, as far as the demodulation is concerned, take your modulated signal x of t, multiply it with a coherent carrier which is in phase and frequency synchronism with the incoming carrier, and pass it through a low pass filter, and you will get your Bessel signal back. Is that obvious? Look at in the frequency domain, it should become obvious. When you are multiplying with AC cosine omega ct, remember what is the operation you are doing? You are carrying out a frequency translation by minus Fc and plus Fc. So let us say you have this component. When you translate it by minus Fc, what happens? It comes here, and this portion comes here. So you get this baseband spectrum that you wanted, and the plus Fc component goes to in the neighborhood of 2Fc, right? Which will be eliminated by the low pass filter. So there is absolutely no difference in the demodulation process. It remains the same. Are you all with me? So the demodulator remains exactly the same that we had for DSPSC. Just apply frequency translation theorem onto this spectrum, and you can see that your baseband spectrum comes back, along with a component around 2Fc, which will of course go. And the same argument you can repeat when you retain the lower sideband rather than the upper sideband. Please convince yourself that if you retain the lower sideband, transmit the lower sideband, once again the same demodulator would reconstruct your message signal back. Okay? So whether you are transmitting the upper sideband, the lower sideband, or the double sideband, your demodulator remains the same. We'll start from this point next time. Thank you very much.